Okay, this video is your first intro to being able to solve problems where forces change. They vary based on velocity. And to do that, we need to understand what a differential equation is. Differential equations are types of equations that contain an unknown function and some of that function's derivatives. And I'll show you an example of that here in a second. We will solve very simple differential equations. Your fourth college calculus class, so your fourth semester of college calc, spends the whole semester solving types of differential equations. So there's a large class of these, lots of applications to them, but we're just going to look at one. Something to be aware of: the solution to a differential equation is another equation. So we're going to be solving an equation to get an equation. This is different than just solving an algebraic equation. If you have an equation that's, I don't know, maybe something like y equals, or 3y equals 10. If you solve this for y, you get y equals 10/3. And that's a number. So your solution is a number. The solution to these equations will be another equation. And our types of differential equations will be what are called separable differential equations. And separable differential equations have a specific way to solve them. I just want to show you one example of this, and we'll look at one example in physics before we get into terminal velocities. So these are the steps. It'd be worthwhile for you to write these down. The first thing you want to do is identify the variables and the constants in your differential equation. It's important because we're going to be separating these variables on different sides of the equation. That's step 2, to separate each variable and its derivative on the same side of the equation. Once they're on the same side, you can integrate both sides. Integrating them will remove our derivatives from it, and then we get to solve the resulting equation for the variable that we care about. And I want to show you one example of this. I just pulled this one off the internet, but this would be a differential equation. It's a differential equation because we have, these would be two functions. So we have an x and a y, or two variables here. And those two variables have their derivatives. Here's our derivative of y, and here's our derivative of x in the same equation. And so the first step is to identify, do we have any constants, and what are the variables? We identified our variables here. There are no constants in this equation. And we've moved to step 2, start separating your variables. You want your variables to be on the same side of the equation, and right now we have dy and our dx on the left and nothing on the right. So the way to separate these, we want dy and y on the same side and dx and x on the same side, and you want your derivative to not be in the denominator. So you'd multiply this dx on the other side. So here's your steps. They move the e to the x on the other side. You can separate e to the x by adding your powers, same as multiplying the e to the x and e to the y. At this point, I want the dx to be with the x and the y to be with my dy on the y side. So they move the dx over, and this is step 2 is done. This would be an equation where we have our variables, dy and y, on the same side, and our x variable with its derivative on the other side. At that point, you can integrate both sides. The integral over e to the x will give us negative e to the x again. Our integral of 1 over e to the y is either negative y, and they integrate these guys, add and c. After you integrate, that removes our derivatives, and now we can solve for whatever function we care about. In this case, they wanted to figure out what is the function of y that satisfies this original equation up here, where the derivative of y plus e times x plus y equals 0. And the solution, if you solve this for y, it comes out to y equals negative natural log ex minus e. You will not have to do all of this stuff. I just wanted you to see those steps. We will do that with a very specific case that you'll get practice with and be able to repeat, hopefully. So let's look at a very simple case of this with physics. So a very simple physics example would be this. Let's consider the function, our velocity function, and velocity equals our initial velocity plus acceleration times time. So we're going to do a very simple equation here, and we're going to do this with a constant acceleration. So this is our kinematic equation. And from this, I want to be able to figure out what is my function of x. We're going to solve this to figure out what is function of x. We already know how this works. We take the integral of both sides, but let's try to break this down so it looks like a differential equation. To do that, we're going to rewrite our v here, and v is just the rate of change. It's the change in x over the change in time. And then we get v0 plus a times t. Let's identify our variables here. Now we have a differential equation. And if we identify the variables, our v0, this is a constant. It's a number. It's not changing. Acceleration is constant. And that's just a number. But our time here, this is our variable, our independent variable. And then x would be our dependent variable. And there's no x in our equation. There's just the derivative of x. So we are going to separate our variables by getting all the x's and the dx's on the same side. And that's really simple in this case because we just have dx. And we want all of the t's, the independent variable, and all of the dt's on the same side. And to do that, all I have to do is multiply by dt on the right side. So I get dx on the left side. I get v0 plus a times t dt. And I've separated my variables. At this point, you could integrate both sides. We will do, at least I will just do indefinite integrals. The sheet that you have to read for differential equations has definite integrals. You can do it either way. But the integral of dx, these undo each other. This function x plus a constant. Dt, you could distribute this into both of these and do two separate integrals, or you can just do it as one integral all at once. The integral of a constant with respect to time is going to be that constant times time, plus the integral of t raised to the first power. We get 1/2. It's constant times t to the second power, and then we get plus c here. And I can simplify this a little bit farther if I subtract c from this side and subtract it on this side. This would be like a c1 and a c2. Whoops, it would be c2 minus c1. So this is just a constant. So the whole equation can have one constant on the right side. And this will be useful for us later when we look at more complex examples. But the only thing that's left on the left side is x, and x is a function of t, which is what we wanted. We wanted to get a function from our differential equation, and our function would be v0 times t plus 1/2 a t squared, and this should look familiar to you. This is our kinematic equation plus the constant c. What is our constant? Well, at x with 0 in it, well, 0 for my time here will give me 0. 1/2 a times 0 is 0. So x of 0 is just equal to c, and so the constant is my initial position, and I could rewrite this equation like this. I'll write it in the form that we have seen before. My constant out in front plus my initial velocity times time plus 1/2 a t squared. And you might say, why do we do all that work to get this equation since we already know it? And don't we just take the integral of this side, and we know in our heads that the integral of velocity with respect to time is our position? The answer is yes, we do know that. And the reason we know that is because of this differential equation. So this is the proof showing that the integral of your velocity equation gives you your position equation, only for a constant acceleration. So that's one example, a very simple example for physics. We will do that with forces and accelerations with terminal velocities.